Okay, so there we go. We have shown that tau prime includes these two sets that you have to have, preserves finite intersections, and arbitrary unions. So far, so good? Now, what I want to do next, I'm going to prove a part B. Oops. Oh, is this okay? Okay. Sorry. Let's erase this side here real quick. So for B, what I want to prove, so here's a definition before I state part B. You guys are going to totally knock this one out of the park, I think. If I have a function from x comma tau to y comma tau prime, which is what we now have, okay, right, that this is continuous if and only if. What do you think the definition of a continuous function between topological spaces should be? In other words, what should be the chapter 3 definition of a continuous function?
The pre-images of taus are open? Or I mean the... How do I word it?
You're taking the pre-images of something on tau prime, right? So the pre-image of a set in tau prime
is in tau.
In other words, I'm just going to say it the very colloquial way, which is I'm just going to say pre-images of open sets should be open, right?
Yes.
So pre-images of open sets are open. Isn't this amazing how much we're taking advantage of the proposition 8 from chapter 2?
Mm-hmm.
The definition of an open set in chapter 2 involved the P and the Q, and we had these neighborhoods and everything. We can't use that anymore in chapter 3. But we can still just adopt this, which was one of our propositions. We can adopt this as our definition of a continuous function between topological spaces, and it totally makes sense. So what we're going to do here in part B is we're going to show that this function up here, where we defined the tau prime topology by looking at pre-images of the sets to see if they were in tau. If you concoct your topology on Y in that way, then your function is continuous. So show that F is continuous. Oh, well, this is going to be rather silly. I only need this much room. Okay, here's my definition. I have to start with an open set. In other words, I have to let U be an element of tau prime, right? That's an open set in Y. My goal is to show that the pre-image of that open set is open. Well, the pre-image of that open set is that. And for that to be open means it needs to exist in tau. But that was my definition. I said something lives in tau prime if and only if its pre-image is in tau. I'm done. That's my whole proof. You've actually created the topology tau prime to be exactly what it needs to be to make this function continuous. It's like completely a trivial thing to prove at that point. Okay, sweet. All right, let's do a part C. Prove that tau prime is the finest topology on Y for which F is continuous. So we have to remember what it means. So we did this in the group work actually on Wednesday. what does it mean for like one topology to be finer than another? So just recall, this is from the group work, that
The finer one is the coarser one's a subset of the other.
right, exactly. So tau double prime is finer than tau prime if tau prime is contained in tau double prime. So a finer topology is going to be one with more sets in it. Okay, it's going to have more sets inside of it. So like when you did the topologies on the set 1, 2, 3, like this would be the coarsest one, as the least things. This topology, this topology is finer than this one is, right? So, because it has more things in it. Most people did good on that problem, except that some people had, like, did this as a topology. It doesn't work because it's not closed under. So X was 1, 2, 3. This isn't even closed under unions. You take the union of these two, you get the set 1 and 2. It's not there. So there were about 3 or 4 people that had that, and they had somehow they came up with 29 topologies, I think, because I told them that was the answer. But this was one of them, which means they were missing something else that was supposed to be there. But just be careful; it's got to be closed under. That would make a good test question. Find all topologies on 1, 2, 3 that are finer than, and then I give you a topology. I would give you one topology, and then you have to find the ones that are. Out of those 29, which of them are actually containing the one that I gave you? That's an idea.
I like it.
I always think of these test questions while I'm doing the review sessions. It's always funny how that works. That's why I never write my exams until after the reviews, because I always get ideas during the review as to what to ask. So anyway, let me see. So okay, so this is what we want to show. All right. So let's do the proof here. Suppose. Let's suppose that we have a topology that is finer than y prime. So suppose that tau double prime is finer. Actually, let's say strictly finer than tau prime. So strictly finer just means it's like bigger, strictly bigger than tau prime. There's something in tau double prime that is not in tau prime.
So when we say if it was just finer, it could have been like with our 1, 2, 3 example, if they just were both.
They're the same. If they're the same topology.
Would it be if they're the same size but not the same?
No, it has nothing to do with size. It has to do with containments.
Okay.
So, but it is true that a topology is considered to be finer than itself. So. Well, that's because every set is a subset of itself. So I want to get away from that here and imagine that I had something that was actually strictly more fine than tau prime was. What I'm going to try to claim is that this function would not be continuous anymore. Right? The finest topology that makes f continuous is tau prime. So suppose we had an even finer one, right? How do you think we're gonna do this?
By way of contradiction.
Okay, suppose f is continuous. So we're trying to prove that. So suppose we have a finer topology, and f from x tau to y tau double prime is continuous. Suppose that you could make that work. Okay, suppose that that would be continuous. This is not going to be possible. That's what we're proving. Okay. So, how do we do it? This is very short. How about we come up with an open set whose pre-image is not open? That's the best way to show that it's not continuous, right? Start with find an open set that has a pre-image that's not open. How do we get an open set to start with? What open set should we use?
Any set in tau prime can work.
Well, so we want to start with an open set and then take the pre-image of that and have it not be open. So should my open set be on the x side or the y side?
And the y side?
The y side, right. So we should pick something in tau double prime, right?
Right, yeah.
So consider u in tau double prime. So we have an open set here. The pre-image of it, is it going to be open? Which pre-images are still open?
The ones in tau prime.
Right. If we start with something in tau prime, then the pre-image of that is open in tau. So I don't want to just pick any old open set in.
It's a U that exists in tau double prime but doesn't
But that's
exist.
not.
That's the idea. You need to pick some. Remember, we're supposing tau double prime is strictly finer than tau prime. That means that we can find this set, right? So such U exists since tau prime is strictly, I'm going to use an emphasis on that there, tau prime is strictly contained inside of tau double prime. There must be at least one set here. Okay? So this is an open set in y comma tau double prime. But then let's look at the pre-image of it. So then the pre-image of that open set, right? The question is, does it belong to tau? Well, the answer is no, because u does not belong to tau prime. So this is not in tau, since u is not in tau prime. Remember, tau and tau prime, these are sets of sets, right? So here's a set that is not in tau, right? And that's because u was not in tau prime, okay? So f is not continuous, and that's a contradiction if you want to think of it that way. We said suppose that f is continuous, but now we're seeing that it's not. So, okay, is everybody all right with this? So in chapter 3, you guys are ahead of everybody else in the class. The definition of a continuous function in chapter 3 is just that pre-images of open sets are still open. It's pretty simple. Okay. So that problem actually isn't that hard. There's a lot of little things to check along the way, but there's nothing where you have to come up with a clever idea for it. It just kind of follows. You just kind of follow the definitions and chase through some calculations, and it comes through pretty easily. Let me give you another one that maybe we'll have to think a little harder. We'll see. It's kind of along the same lines here. So I've only got two more problems to do. So we'll should be done by 4. So let's try this one. Suppose that f goes from x to y. Now I'm not mentioning any topology yet, but let's suppose that this is onto functions. So we're going to need to use that. And x has the trivial topology. This would be, basically just saying that tau is just the empty set and the whole thing. Remember, the trivial topology is just those two sets. Okay? So then I have 2 parts here. The first part is to prove that f is continuous if and only if Y has the trivial topology as well. So in other words, tau prime is just the empty set and the whole space Y. So in order to have a continuous function here, Y has to have a very simple trivial topology. Remember, the definition of continuous is preimages of open sets are open. If I do this, there aren't very many open sets. These are the only two. And all you have to have a continuous function is that preimages of these two sets have to be open. Functions where you have a trivial topology on this side and a big topology on this side, like the discrete topology, there's a lot. In other words, if you think of it this way, functions where the tau is a large topology with many sets in it, and the tau prime does not have very many sets in it, those tend to be continuous because you're taking the preimage of not very many sets. You don't have that much to check, and there's lots of open sets in the X space that could be the preimages, right? The other way around, right? Imagine that X has a very small, like a trivial topology on it, right? Then in order for a function to be continuous, if this is your topology on your domain, it's going to be hard because the preimages of your open sets here have only two choices here, right? So in order to make a function continuous, when you're starting with the trivial topology here, you have to have a very small topology on this side. I just want you guys to think intuitively about this, that continuous functions generally are going to have big topologies here, small topologies here. Because who knows, maybe someday I'll ask you to give me an example of a continuous function or a function that's not continuous, and you have to create something. Well, to create something continuous, make a big topology here, a small topology here. Maybe I should be writing this down. So F continuous. I'm not going to make a very precise statement. I'm just going to say here, make tau big and tau prime small. So tau has lots of things in it. Tau prime does not have very many things in it. And if you want F to be not continuous, then you want to make tau small and tau prime big. Okay, this is just a rough statement, like a rough thing kind of to keep in mind. Okay? So this is just useful, if you ever want to make counterexamples to things or whatever, this is probably a good idea. Okay. So now let's start working on the problem. So let's see. We have an if and only if here. Do you guys want to prove the forward part first or the backwards part first? Okay, I guess I'll decide. I'm going to prove the backwards direction first. Nobody has a strong feeling here. That's fine. Okay, let's go backwards first. Let's suppose that tau prime is the empty set and capital Y. Suppose we have the trivial topology on the, or what we sometimes call the indiscrete topology on Y. Okay? To show that F is continuous, I have to prove that the preimage of any open set is open. These are the only two open sets that I have. So I'm simply going to note that I'm just going to literally take these two pre-images. I'm just going to figure each of these things out, right? And hopefully come up with something that's open. What's the pre-image of the empty set? Empty set. And what's the pre-image of all of capital Y? X. Right. These are both open, right? So this is in tau. This is in tau. So all pre-images of open sets are open. Yay. Looks good. Okay. So that's the backward direction. What did you notice about the backwards part of the proof?
Because you have to set it's onto, right?
Yeah, we didn't even use that, did we?
Yeah.
We did not use the onto going backwards. That must not be important for that side of it. We must need that when we go forward. Okay, so let's go forward and see if the onto comes into play. I always get nervous if I don't use my assumptions. It's like, wait a minute, something's wrong, right? So hopefully we're going to use the onto here somewhere. So let's assume that F is continuous. And then I'm going to claim that tau prime has to be the trivial topology. Okay, so there is some topology on capital Y. I'm claiming it has to be this one. Okay. So, there's no other sets that can be in this topology. Of course, the topology has to have these two things in it. The issue is, could there be anything else in tau prime? We're trying to claim that no, this is the only thing that could be in tau prime. How do you suppose we should prove that these are the only two sets that are in tau prime? Don't try to think where the onto comes in or anything like that yet. It'll take care of itself when it shows
We
up.
assume there is extra, and then we find a contradiction.
Okay, suppose there's some other weird set inside of tau prime.
That's fine.
Right, in other words,
Yeah.
suppose that the topology over here is finer than this one. Okay, so basically, in other words, I'm kind of doing it by way of contradiction. So, of course, the empty set has to be in tau prime, and Y has to be in tau prime. Any topology has to have those two sets in it.
Mm-hmm.
But now let's suppose that there's some other set U that is in tau prime, right? Where the empty set is not the same as U, which is not the same as the whole Y. Suppose there's some other, say a third set somehow. There's some other open set on the right-hand side. Okay? So then, well, if it's an open set and our function is continuous, what can we say about it? What can we say?
Has to be.
So
The reimage.
What can you say about the preimage?
image is open.
It's open in this.
It has to be open in X, right? It has to be in tau.
Right.
Oh, but wait a minute. Tau only has these two sets in it. So, either the preimage of U is empty, or the preimage of U is the whole X. And I claim that those are both impossible. If the preimage of U is empty, it means nothing gets mapped to U. If I draw a picture, here's X, here's Y, and U is maybe right here. If the preimage of U is empty, it means that anytime you look at this function, right, you never, there's no arrows going into the U, right?
But,
Can that happen?
yeah, because it's not right.
Because the function is onto, everything in Y has to get hit by an arrow So that includes everything that's in U, and U is not empty, so there's something in there, right? So this is impossible since F is onto. So there comes the onto. We knew it was going to show up eventually. What about the other possibility over here? I'm going to redraw this picture. X and Y, and here's U inside of it. If the preimage of U equals capital X, what that means is that every single thing in X goes into U, right? Every single arrow, all of the... Sometimes these pictures can be amazingly helpful, right? That's my picture. The preimage of U is everything. All elements of capital X end up in U. Is that possible? There's going to be some point out here, right, that's not... Remember, notice that U is not the whole space Y. There's going to be some point out here that wouldn't be in the image of the function. And again, this is impossible since F is onto. Okay. Impossible since F is onto. Is that camera still doing okay?
Yes.
Okay, super.
4 more minutes.
Okay, in 4 more minutes I have to change to another memory card. Okay, does that make sense, guys? So, thus my claim is true, and thus tau prime is trivial. Alright. This is really good practice with the basic chapter 3 stuff. Okay, perfect. Okay, then I have another part B here, real quick. I have a part B, and then I have one more problem to go over with you, and then we're going to call it a day at that point. Okay? So, part B just says, show that A is not true if the function is not onto. Show that A fails if F isn't onto. So in other words, if your function is not onto, then it is possible for this if and only if to fail. So we need an example. So these make good test questions too. Give a little example of something. Something like this, you could actually just, you could just do this, since we're very familiar with this one from the homework, you could literally just like try to make a picture here. Something like this, with the set 1, 2, 3, because you kind of know what the topologies are. So we're going to assume that tau is just the empty set in capital X. And can somebody, before I put a topology on Y, let's not do that yet, can somebody just give me a function here that would be not onto? Because I'm trying to come up with an example if the function is not onto and something happens. So can somebody kind of, we need to just draw some arrows here. Right? So we'll just pick on 3 people to help me with this. Vin, where do you want to send 1 to?
1, 2, 3.
1
to 1, right?
1 to 1. Okay, great. Olga, where do you want to send 2 to?
3.
3. Okay, Hung, where do you want to send 3 to? 2. Don't do that.
No.
I want a function that's not onto.
Oh, 3 here. 3.
Sure. Okay, as long as you have to at least leave something blank on the right side. Okay, so let's just make that function. Okay? So can we sort of like, we want this to be like not true. So either we're going to stick with the trivial topology. Well, but wait a minute, when we prove the backwards part,